Okay, so I know everybody. I'm going to be talking today about structural equation modeling, which is one of my favorite topics to talk about. So a brief introduction for research consumers, or maybe I should title this, why you should know about structural equation modeling, and or why it's important and what you need to know in order to be an effective consumer. So, everyone in here, I think, well, how many are, everyone has read articles that discuss factor analysis and confirmatory factor analysis, correct? You had to for me, right? I'm assuming many of you have read articles that use structural equation modeling. A few of you are doing structural equation modeling. So, I'm hoping that at least from this you'll get a little taste of what it's all about. So I'm going to assume that you have a basic understanding of multiple regression analysis, that you're generally interested in statistical research topics, and I'm mostly going to focus on giving you an understanding of SEM that will help you read and critique the SEM studies that you do. So this is a sample structural equation model, and it looks pretty complicated, or pretty fantastic, however you respond to it. But let me just give you a sort of way of thinking about what this is. And so the general purpose of structural equation modeling is to determine the effects of one or more influences on one or more outcomes. And so in this model right here, the primary things of interest are the effects of out-of-school homework on achievement as measured by grades versus in-school homework on achievement as measured by grades. And then there are two background variables that we're interested in controlling. I also want to point out that this is structural equation modeling, which is important to think about. And so what it boils down to is this enables you to model a system. So, I mean, I talked about the main things we're interested in is that effect and that effect. You can see there's a whole system going on here. And if you can model, it allows you to model this system of influences and outcomes. And so what this means is if you have an idea about the way the world works, and you can collect data to measure the constructs that you're interested in, you can determine whether or not you may be right or not. You can determine whether you're right that out-of-school homework has a larger effect on achievement, say, than in-school homework, or that you think that this influences that via some other construct. So modeling, the whole notion of modeling, I think, is very important and very powerful. Okay, so I'm going to talk a little bit about jargon. We're going to start talking about path analysis. It's the simplest form of structural equation modeling. Causal inference, confirmatory factor analysis, and so on. Then I'm going to tell you how you go about critiquing SEM studies. So a little jargon. So I'm going to refer to this as structural equation modeling, which is a pretty common term, but it can also be referred to as analysis of covariant structures. Sometimes you hear people refer to it as causal analysis, sometimes LISREL, which was simply the first computer program that enabled you to do structural equation modeling. Structural equation modeling involves what I'll refer to as latent variable structural equation modeling. And it's also a subset of it is confirmatory factor analysis, and another subset of it is path analysis. The path analysis is simply the simplest form of structural equation modeling. It uses measured variables. You'll understand what those mean in a minute. And it's going to be our point of starting a discussion, because you can actually solve path models using multiple regression analysis. Okay, so I'm going to start with a very simple path model. And here, my interest is in, primary interest is in the effects of academic motivation on academic achievement. And this is an example I used in this book. So we start out with a model. And so, as I just said, my interest is the effects of academic motivation on academic achievement. So I show that in this diagram by having motivation, academic motivation, influence, and we signify the influence by an arrow, influence and achievement. But for whatever reason, we also think it's important to have cognitive ability in the model. And one reason we would think that would be important is that if you look at school learning theory, you'll see that all school learning theories have some sort of variable, some sort of construct that gets at cognitive ability. And the notion is that cognitive ability is also an important influence on achievement. Okay. And I'm signifying that by this arrow here. And I think that cognitive ability may also influence motivation. So, I think that kids who are smarter are going to have higher levels of academic motivation as a result of that. And I could also turn to research. So if I looked at research, for example, on motivation, I might find that, yeah, there's some research that suggests that ability influences motivation. Well, so I can define these variables a little bit. And actually, this is how these were defined. So I defined academic motivation as interest in school, willingness to work hard, and post-high school educational plans. And I want to point out that while that would be something that you could probably change, it's certainly not something that you can manually assign. You can't say, okay, Gabrielle, you're going to be highly motivated, and Jameson is not going to be highly motivated. So, achievements measured by tests in reading, math, science, civics, and writing, and cognitive ability is measured by 2 verbal ability tests. And this, one way of thinking about what ability is all about is it's what we often think of as a control variable, and what I'm going to call a common cause. It's, at least if it pans out the way I have it here, ability is a common cause of achievement and motivation. So I go out and I measure these variables, and then here, these curved arrows, double-headed arrows, signify correlations. Here are the correlations among these 3 variables. Well, we're not interested in correlations, we're interested in effects, right? Well, interestingly, so I now have 3 unknowns, these 3 paths, and I've got 3 knowns, these 3 correlations. And if you remember your high school algebra, you could use the correlations to solve for the paths. Fortunately, we don't have to remember our high school algebra because you can also solve this using multiple regression analysis. And you simply regress achievement on ability and motivation, the 2 variables that point to it in the model. And you regress motivation on ability, the 1 variable that points to it in the model. And the regression coefficients, either standardized or unstandardized. Here I'll use standardized, but they're both used. The regression coefficients represent those paths. So here, for example, are the regression results. So here are the coefficients, standardized, pointing to achievement. Here are the coefficient from ability to motivation. And then there are the unstandardized coefficients. And now I can stick those in the model. And here are the standardized effects. And so what this is saying, if you know how to interpret regression coefficients, you know that one way of interpreting this would be to say, okay, so for each one standard deviation increase in motivation, achievement will increase by 0.108 of a standard deviation, other things being equal. Okay? All right, so that's our potential interpretation. The interpretation is this is the effects of motivation and ability on achievements. And keep in mind that this is always given the validity of the model. So we'll spend a little bit of time talking about what makes about a model valid. But keep in mind this famous quote, all models are wrong, but some models are useful. So this model is no doubt wrong, but hopefully it's not too far wrong. Okay, so let me add a few more aspects to this model. We have here what are known as disturbances. And what these represent is all of the other influences on these variables that are not in the model. So obviously, ability and motivation are not the only things that influence achievement. You could probably come up with 24 things off the top of your head that influence achievement. Well, we don't know what all of those other influences are. And so we represent those by this D2, which stands for disturbance. We don't measure all those other influences, and we signify that this is an unmeasured variable by enclosing it in a circle or an oval. And then also we know that ability is not the only influence on motivation, so motivation also has a disturbance. So these disturbances represent all of the other influences on the outcome other than the ones shown in the model. They're not measured. We don't know what all those other influences are. And if you have taken correlation regression, you would know these as either residuals or errors. Why do we name them something different? Instructional equation modeling? To confuse graduate students. Okay, but wait a minute. Haven't I just used correlations to infer causality? Shouldn't this lead to my excommunication from the Church of Statistics? That was the very first rule you learned in statistics, right? Okay, well, let me give you a little true-false question, quiz here. So you don't have to answer out loud. So think to yourself whether you would answer this true or false. We should not infer causality from correlational data. I'm guessing many of you would say true. Or maybe you will go for a less severe sort of statement. It is inappropriate to infer causality unless there's been active manipulation of the independent variable. Again, I'm guessing that many of you would say true. So how about this one? Smoking causes lung cancer in humans. I would say true, but we haven't randomly assigned human beings to smoke or not to see whether they get cancer. So, if you want to say true to these, you better say false to this, or if you want to say true to this, you better say false to these. Divorce affects children's subsequent achievement and behavior. Again, I'm not aware of any studies where we've randomly assigned parents to get divorced to see what happens to their children. Personality characteristics affect life success. The Earth, it's not just social sciences. The Earth's gravity keeps the moon in orbit around the Earth. Well, I'm not aware of any studies where we've randomly assigned a gravity to the Earth to see what happens to the orbit of the moon. My point is simply this. Even though we pay lip service to these statements here often, time and again we do make causal inferences using correlational data. And if we had more time, I could talk a little bit more about this example here, but and it's not just a social science issue either. It's an issue that cuts across lots of different sciences. My point is simply this. We do indeed make causal inferences using data that are non-experimental in nature, And so what would probably be more appropriate is for us to figure out when we can do that accurately, when we can make valid inferences, and when we don't make valid inferences. And we can use that to improve our non-experimental research. And then one more. Research in sociology, economics, political science is intellectually bankrupt. I mean, occasionally, many of you will come up with experimental research that you can do, but research in these social sciences is largely non-experimental in nature. Okay, so again, my point is simply, we need to broaden our thinking a little bit. So this is another great book in regression, multiple regression analysis, Cohen and Cohen, from their second edition. And what's interesting is in the first edition, they indeed made statements like this, and by the second edition, they're saying, well, maybe not. So, okay. So, but I'll also point out to you that it's not the case that we made causal. We didn't make the causal inferences from the correlations. We didn't see the correlations and say, oh, well, this affects this. In fact, we made the causal inference when we drew the model in the first place. And if you'll recall, I referenced things like theory and previous research in order to draw those arrows. And so what we're doing is we're making causal inferences based on theory and research, and then we're simply using the correlations as the fuel for the calculations to figure out whether, given the adequacy of our model, what are the magnitude of the effects. So, without going to a lot of detail, I'll simply address the issue of, okay, so given the adequacy of the model, I said before, given the validity of the model, I think, what makes a model adequate? Well, two things. The single most important thing is that you include the important common causes of your presumed cause and your presumed effect. And then second, and believe it or not, this is not as serious a violation as the first, but the second, you've got the paths drawn in the correct direction. If you do those things, then it's perfectly valid to make causal inferences using correlational data. These can be hard, though. How do you know you've gotten all the important common causes? Okay, so how did we make the causal inferences? Well, we made the causal inferences when we drew the model, and we based it on theory. I talked about school learning theory. We talked about previous research. You can also use time precedence, and this is something that applies to the current model, even though perhaps you measured cognitive ability and motivation at the same time. We also know that cognitive ability is extremely stable over time. So cognitive ability at, say, age 12 is going to be very similar to cognitive ability at age 6. So we can think, okay, so that probably precedes the other variables in time. And previous research and just plain logic thinking, okay, would it be more likely that motivation would influence achievement, or would it be more likely that achievement would influence motivation? Also keep in mind that when I say cause, I'm not saying that one variable directly affects another. It's a probabilistic statement, meaning that if you're highly motivated, chances are you're going to be a higher achiever. Okay, so let's go back to our very simple model. So what this means is this gets at the effects of motivation on achievement given the validity of the model. And what this means is that for each standard deviation increase in motivation, achievement increases by 0.108 of a standard deviation, other things being equal, and given the validity of the model. That ability has an effect of 0.715, so each standard deviation increase in ability leads to a 0.715 increase in achievement. And ability also influences motivation. So kids who have higher levels of ability, as a result, have higher levels of motivation. One fascinating and important aspect of a model like this is that it is also a way of looking at indirect effects, which are very important. And so we can use this model very simply to calculate the indirect effect of ability on achievement through motivation. And it's simply do it by multiplying those two paths. 0.205 times 0.108, the indirect effect of achievement on, ability on achievement through motivation is 0.022. If that were larger, I mean that's pretty small, but if it were larger, we would then be able to make statements like, okay, so how does ability affect motivation? Or how does ability affect achievement? Well, maybe it affects achievement via motivation. Maybe kids who are smarter are more motivated, and that higher level of motivation also results in higher achievement. In this case, it's pretty small, so there's very little indirect effect. We can do that and go back to our cancer and smoking example. You might say, okay, yeah, so I think smoking does affect lung cancer. How does that work? Well, one way it might work is that smoking leads to tar buildup in the lungs, and tar buildup in the lungs leads to cellular change. And so what you're saying there is, there's an indirect effect of smoking on tar buildup, and an indirect effect of tar buildup on cellular change, and that's what's influencing the existence of cancer. We know this as either indirect effects, or you probably hear it referred to a lot as mediation. This is a way of testing mediation, and you can test these indirect effects for statistical significance, and there are a variety of ways of doing so. You can also add the direct effects to the indirect effects to get the total effects. Okay, just a little more jargon. This model is what is known as a just identified model. The easy way to think about that is we have just enough information to solve from the past. We had 3 unknowns and we had 3 knowns, and so we had just enough information to solve for the 3 paths. It's also possible to have an over-identified model, and an interesting thing happens when you have over-identified models. If you're using algebra to solve for these paths, you can come up with 2 equations for both A and B. And that might seem like not a good idea, but it actually is an important aspect of structural equation models. Okay, so I said that we could solve for the paths using the correlation, actually the covariance matrix, but let's say the correlation matrix. You know, you can also do the reverse. In this model right here, I could use these paths and figure out what the correlations were. Well, when you have an over-identified model, those 2 matrices, the matrix of the actual correlations and the matrix of correlations that were implied by the model, are going to be different. And so, if you think about it, if you did that and you looked at the actual matrix and the implied matrix and they were very similar, that would probably tell you something good about your model, right? On the other hand, if you've got very dissimilar matrices, you know, the matrix implied by the model is very different than the actual matrix, that would tell you, something must be wrong with my model. And that comparison there is the genesis of all the fit statistics that you see in confirmatory factor analyses and structural equation models. And so this issue of over-identification, while first seeming like a problem, is actually a blessing. And so you're still getting deeper and deeper into the jargon here, but the degrees of freedom in a structural equation model tell you the degree to which the model is over-identified. Larger the degrees of freedom, the more the over-identification, and the more parsimonious the model is. And simply note that unlike all the other statistics you've learned about so far, that degrees of freedom are not related to sample size in structural equation model. It's related to the degree of over-identification. And I just now want to tell you, these slides are actually up on Canvas if you want to use that. Okay, a little more jargon. We use curved lines to represent correlations. One-headed arrows represent presumed influences. Rectangles represent measured variables, also called manifest variables. Ovals represent unmeasured variables, also known as latent variables. And this is not jargon that you need to know as much, but for some reason we call the presumed causes exogenous variables and the presumed effect endogenous variables. Why do we do that? Keep you confused. And then disturbances are unmeasured variables. They're in the circles or ovals. And they represent all of the other influences on your effect or your endogenous variable, beyond those that are in the model. So again, just identified model, you got just enough information to solve for the paths. Over-identified models, you have more information than you need to solve for the paths, and that allows you to get feedback as to the fit of the model to the data. We'll come back and talk a little bit more about fit. Well, okay, so we've talked about path analysis. And as I've said, it's the simplest form of structural equation modeling. It is a great way, I think, about thinking about multiple regression, in that it allows you to think about a system of variables. Before I go on, any questions? Yes, Morgan?
Could you describe again a little bit about over-identified and what it would mean to have more than enough info to solve for the path?
Okay. Well, so I'll start by saying the same thing I said before. So I said that one way that you could use the correlations to solve for these three paths, right? Okay. And so what you do is you get three equations and one equation for A, B, and C. And there's some rules on how you generate those equations. If you had an over-identified model, say without that path, you said, you know what, I think that ability influences motivation, and ability influences achievement, but achievement has no effect. I'm sorry, motivation has no effect on achievement. Well, you still got three correlations. You got the correlation between these three variables. So you got three knowns, but now you only have two unknowns. And as a result, if you were solving this via the equation, doing it by hand, you could come up with with two equations for solving for A and two equations for solving for B. In reality, what happens is what we do is the structural equation modeling programs solve for the paths using the correlation matrix. So you got 20 variables, you got a big correlation matrix, and it uses that to solve for the model. And then once you have a model with the estimates in it, you can do the reverse. You can take those estimates there, those paths, and you could use those to solve for the correlations. If you have a just identified model, those two sets of matrices are going to be identical. But if you have an over-identified model, they're going to differ to some degree. Yes, Steph?
So one thing I've never really understood very well is like if you're using the correlation matrix from your sample of data to find those paths, and then like then you reverse it, how can you get a different answer if you're using the same data? Like if I times x by 2, then x divided by 2 is the same. That's kind of like what I'm thinking.
Well, so assuming the model is just identified, they would be the same.
Oh, okay. It's because you have the uncertainty of like which one. I
Mhm,
got it.
mhm. But just think that if we didn't have this path here, and we said, okay, so given that model right there, what is the correlation matrix that it implies? And what that would be it would imply a correlation of 0.715 between ability and achievement, a correlation of 0.205 between motivation and ability, and a correlation of 0.205 times 0.715 for this correlation. And just keeping in mind those first two, you can see, well, maybe you can see that, that's not quite accurate. We estimated that correlation at 0.715, but it's 0.737. So already we've got a difference between the actual correlation and the predicted correlation.
So if you had a more complicated model that was even more over-identified, then you have like more possibilities of what the matrix could be. Okay.
Yes. Mm-hmm. Yeah, with a very simple model like this, which would only have one degree of freedom, and there aren't too many correlations that are going to be that different.
So then when you're like calculating fit statistics or like saying like how good your model is, when you have, is that like based on every single possible correlation matrix for those particular variables? Or you don't have to answer that.
It's based on the entire correlation matrix, but where the differences come about are going to be based on where the model is over-identified, where there are paths that you could have had that you didn't have.
Okay.
So do you typically start off over-identifying it, or do you do the just identified and then move to over-identified?
It's better to start with the over-identified if you can, because then you're actually testing hypotheses. And so I'll talk a little bit more about fit and how that comes into testing hypotheses in just a second. Maybe it'll become clear. Well, there's a problem with path analysis, though, in that one of the assumptions underlying multiple regression is that the variables in the model, and especially the causes, are measured without error. Well, we know that doesn't happen very often in the real world. And it's also the case that measurement error in general can distort estimates of effects. And, well, there are very few variables that are error-free. So what are we going to do about that? You guys actually already know a way of dealing with that, and that is the method of factor analysis. And so here is a confirmatory factor model of the factor structure of the DAS. What this is getting at is it's saying that, okay, the DAS has 12 subtests, but these 12 subtests, in fact, really just measure 4 underlying constructs: verbal, nonverbal, spatial, and memory abilities. Just a little bit of more understanding of what we're talking about in a factor model. We're saying these variables in circles or in ovals are the factors or the latent variables. Remember, we use circles or ovals for variables that are not measured. Well, these are not measured directly. What we're doing is we're inferring them from these three variables here, and we're inferring this factor from these three variables here, and so on. So these are the factors or latent variables. These are the measured variables. And just to fill this out a little bit more, measurement error are these little circles over here. We often refer to these as factor loadings. And those curved double-headed arrows represent the correlations among the factors. One way of thinking about this is, okay, you got these three tests, and so we think they measure underlying verbal ability construct, and these factor loadings tell us that, yeah, they do a pretty good job of that. Or another way of thinking about what this says is that there's something inside a kid's head that we'll call verbal ability that causes them to score a certain way on naming vocabulary and word definitions and verbal similarities. Those are both decent ways of thinking about it. Well, so recall our first SEM model. It's starting to look a little more similar now, right? Well, in fact, the only difference between this and this is that with this model, we simply have correlations among the latent variables, whereas with this model, we have paths among the latent variables. And remember what the paths represent as the presumed effect of one variable on another. And so we could go back to our initial homework model and start out with a confirmatory factor model and just allow our latent variables to be correlated with one another. And what's the advantage of that? Well, what we're getting at then is the correlation between these variables with the effects of error removed from the model. And so the addition, as we go from confirmatory factor analysis to structural equation modeling, is essentially now what we're doing is a regression of the latent variables on one another. So now we have paths drawn among the latent variables. Previously we had paths in path analysis, we had paths drawn among the measured variables. Well, we've just added now paths among the latent variables. So now what we're talking about is the presumed effect of one latent variable on another. So we simply replace the correlations with paths representing the presumed effects. And again, one of the nice things about a structured equation model is we can also look at indirect effects, aka mediation. So very often people will actually do this in steps. They will first start with they'll start with a confirmatory factor analysis of the latent variables, and they'll call this the measurement model. And then they'll add in the structural model, which is the full-blown SEM. Also, why are latent variables better? Well, what you've done is you've taken the unreliability and the invalidity that we know exists in every measurement we make, and we've put that to the side, and now we're interested in getting closer to looking at the effects of the constructs on one another rather than our imperfect measures on one another. So we're getting closer to the effects of true homework on true grades. And so the way you'll know that you've drunk the SEM Kool-Aid, if and when you ever do, is when you start thinking, like I do, that the real variables are the latent variables, and the measured variables are just our imperfect, imperfect measures of those real variables. Okay, some more about fit. If degrees of freedom are greater than 0, then we will have fit statistics. So if the model is over-identified, we'll have fit statistics or fit indices. And it's important to at least have some rules of thumb for judging these, because every SEM article you'll read will talk about fit statistics. And what these represent is the fit of the model to the data. Another way of thinking about that is, could this model have produced the data you got? Okay. It's derived from the comparison of the actual correlation matrix to the implied correlation matrix. And there are multiple, like dozens of different possible fit indices. So in the model I showed you originally, here were several listed: chi-square, TLI, CFI, RMSEA. And there are rules of thumb for judging these. So you don't need to memorize these, but if you want a little cheat sheet for future reference, here is a little cheat sheet. So the CFI is the comparative fit index, and a rule of thumb is above 0.95 is a good fit. The RM, same with the TLI that I mentioned. The RMSEA is the mean square error of approximation. And this, for that you want below 0.05 for a good fit, and so on. So there are some of these various fit statistics. The chi-square is interesting in that everyone will report it, but few people will pay attention to it. The chi-square it can actually be tested for statistical significance. So this is, and as I said, degrees of freedom don't have anything to do with sample size with structural equation models. And it's also the case with structural equation models, you want this to be non-significant. What does a non-significant chi-square mean? It means that the actual correlation matrix and the implied correlation matrix do not differ to a statistically significant degree. Or, in other words, yes, this model could have produced the data we find in the real world, which in turn says, yeah, this model could describe the real world. So what does a good fit mean? Yeah, it means the model could have produced the data. If you have a bad fit, it means you're wrong. If you have a good fit, maybe you're right. So, but that's better than nothing, better than a short sticky guy. Okay. Well, what do you do if you don't have a good fit? And oftentimes, especially if you're starting out in a new area of research, you'll wind up with a model that does not have a good fit. Well, generally speaking, what happens is you make changes to the model. And in fact, the structural equation modeling programs can help you do that through some more detailed fit statistics. But you have to keep in mind that as you do this, you're moving from a confirmatory sort of approach to an exploratory approach. And it's also the case that when you make model modifications, they have to make theoretical sense. And finally, my last admonition, don't overdo it in model modifications. Okay, so now you know how to, at least a little bit, understand how well a model fits the data, what fit means. Well, it's also the case that you can use these fit statistics, and now we're getting more powerful, to compare competing models. So let's say you have two competing theories of how homework works. You can have competing models, each that represents a different theory, and you can compare the fit of those models. And generally speaking, we use change in chi-square for that. Or there's another fit index that is used sometimes called the key information criteria, KIC. And again, here's some rules of thumb if you want to go back and you're reading an article and say, well, how do I make it this? Here's some rules of thumb. Let me just show you. So let's go back to our original homework model. And so here was our original model. It showed a pretty good fit to the data. We wanted this above 0.95, it is. We want this below 0.05, it is. So it's a good fit to the model, the data to the model to the data. I get those confused. It's a good fit for that model. But you know, I'm reading a bunch of stuff in the newspaper. It says, you know, homework really has no effect at all on learning, and it's just a time waster for kids, and we really shouldn't be requiring kids to do homework. So, okay. Well, so we could actually test that to find out whether it's true, and we could test that by saying, okay, well, if that's the case, if homework is really ineffective in producing learning, then this effect should be 0, and this effect should be 0, and probably this effect should be 0 as well. Okay, and so if I go in and tell the model that these effects should all be 0, which is exactly the same as simply deleting the past, I get a model that fits worse. I mean, it still fits okay, but even here you can see that the fit is worse. And we can compare this statistically by comparing the chi-squares and the degrees of freedom. And we see that there's a huge increase in chi-square and a 3-degree of freedom increase, and that is statistically significant. What does that mean? It means that the more parsimonious model, the model in which we said these paths are actually equal to 0, fits much worse than did the model that allowed those effects to exist. And so, bottom line is we can reject that notion that homework has no effects. Okay, so here we have the standardized estimates from this path. So just a little brief thing on how to interpret these. Standardized coefficients, we talk about change in standard deviation units. So this effect of 0.28, what does that mean? For each standard deviation increase in out-of-school homework, grades increase by 0.28 of the standard deviation. And if we had unstandardized coefficients, and I don't think I have a model showing those, this would be a value of 1.2, and that would mean for each 1 unit change in the influence, the outcome will change by 4.2 units. Generally, you report both of those. Okay, so let's revisit causality, because hopefully my little spiel didn't convince you entirely that you should make causal inferences from correlational data. So, okay, so what does this represent? This represents the effects of homework on achievement given the validity of the model. In other words, if this model is a reasonable representation of reality, then yeah, these are the magnitude of the effects of each of these variables on the other variables. And again, what needs to be the case for this model to be a good representation of reality? All important common causes of our presumed cause and our presumed effect need to be included, and the paths need to be drawn in the correct direction. So you see here, I'm just using these terms, causality all over the place, when you think, I'd be raked over the coals if I did that. And so lots of people use the word relationships or relations instead of effects. It seems to me that's sort of dishonest. If you're interested in effects, talk about effects. You can always have a disclaimer like this. So this is out of somebody's dissertation that we put in because we'll be talking about effects. And this explains, in fact, what these coefficients represent. Okay, so here are the basic steps. You develop the model, you make sure that it's at least just identified or even better over-identified. If not, you go back to the drawing board. If it is just identified, you measure the variables, you estimate the model. And then you say, is the model fit adequate? If not, you re-specify the model and go through that. If it is, you interpret the results, consider alternative models, and report the results. Pretty simplified, but that's the basic procedure. Okay, so I said that I would give you some rules of thumb for reading SEM studies, because many of you are going to be doing that rather than conducting them. So the first thing to do, especially so you read this study and you say, boy, I really don't like those results, I don't believe those results, I think they're wrong. How do you figure out if they are wrong? Well, the first thing to do is to examine the model. And presumably you know something about theory in this area of inquiry. So you need to make sure that the model is consistent with theory. Presumably you know something about the previous research in that area. And so you need to make sure that the model is consistent with previous research. Keep in mind the two important questions that you need to always be able to answer as yes. Does it include the important controls, which we now know are in fact common causes of our presumed cause and our presumed effect? And are the paths drawn in the right direction? If you're talking about confirmatory factor analysis and SEM, well, you also want to make sure that the latent variables are well represented. So let's say in one of those, that the DAS model, for example, all of my tests that supposedly measure short-term memory or that measure, GSM are measures of memory span, and I don't have any working memory tests in there. Well, then we would say, that latent variable really shouldn't be called GSM, it should just be called probably memory span. It was not a well-represented latent variable. And one of the rules of thumb, and it makes it much easier to make models work, is that you've got 3 measured variables per latent variable. So as you're reading studies, that's a plus if they've done that. They'll talk about the estimation method. Maximum likelihood is the most common. If they talk about missing data, hopefully they'll be using some sort of maximum likelihood methodology. FIML, it's fun to say, stands for Full Information Maximum Likelihood Method, is one of the best ways of dealing with missing data. Hopefully they report fit statistics. Hopefully they report multiple fit statistics. Hopefully there's a good fit, or at least an adequate fit. You also want to look at whether the factor loadings are statistically significant, whether they're large or moderate in size, whether they talk about their model modifications. How many did they make? Did they make a ton of them or a few of them? Did they compare competing models? Did those competing models test substantive hypotheses? Didn't talk about this, but it's also the case that there are many equivalent models that you cannot differentiate by fit. Did they recognize that those exist? And then, as you read, also you want to make sure they made a substantive interpretation. I've got some rules of thumb that I use for whether standardized paths. So a lot of this research that gets done with structural equation model will use like sample sizes of 3,000, in which case most of the paths are going to be significant. And so very often, or 20,000 often. And so it's sometimes you need some rules of thumb for what's small, medium, and large. Finally is the discussion that's consistent with the results. It's amazing to me how often you read the discussion and it's like, wait a minute, this didn't go with these results that I just read. If you want to criticize the model, here are your 2 primary things to think about. Was a common cause neglected? What does that do? Well, so as you can see in this model here, previous achievement is a common cause. It influences both grades and out-of-school homework. What would happen if we had not included it in the model? If I had not included previous achievement in this model, then the estimate of the effect of out-of-school homework on grades would be 0.58 instead of 0.28. So neglecting a common cause changes the estimates of the effect. Are the paths in the wrong direction? Yeah, what if you don't know what the right direction is? Well, you can actually test those, test the direction of effects with longitudinal data and with carefully specified over-identified model. And are the latent variables correctly named? All right, I'm running out of time. If you want to get more advanced, we can have multi-group models where you have different models for different groups and we can test whether they're equivalent. It's a way of testing the moderation of the interaction. Let's see, there are latent growth models in which you can test whether variables influence growth in a construct or whether growth in a construct influences something else. Here are some resources, some various SEM programs. Amos is the easiest one to use. M+ is the most powerful. And then there's some other ones. R is free. And some textbooks. And I'm not going to do a sample analysis, but maybe I'll do that in research plan if you want to join us. Questions? Oh, Morgan left. I was going to guess we might answer their questions. Hopefully I did. Other questions? Yes, Stephanie.
We've seen a lot of examples that are like intelligence or academic or like education focused. Do you see SEM like moving in or being really important in other areas?
Oh yeah, it is important in other areas. This is where I'm most interested in, so that's where my examples come from, sure. Any area of research where you're doing non-experimental research uses structural equation modeling increasingly, and it's even areas where people are doing experimental research, structural equation modeling can be important. I've got a neat book called Cause and Correlation in Biology, and the guy who wrote that makes the case that, you know, yeah, we can do research where we, for example, try different fertilizers, randomly assign a field to have one type of fertilizer versus another, and see which one leads to more growth. But in order to figure out how that works, mediation, how that works, you have to go to a correlational method in order to figure out what's going on inside the plant. So even lots of people who are doing experimental research are starting to do SEM to try to figure out, oh, okay, so how does that work? What are the mediators? Either crystal clear or so opaque.